You think you know the planets of our solar system. Uranus is here to prove you wrong. This distant, pale blue world is not the quiet giant it appears to be. It is a vault of bizarre secrets, a cosmic oddball that defies every rule we understand. In this journey, we will dive deep into 25 of its most puzzling enigmas, from a planet that rolls around the sun to a hidden ocean of exotic matter. By the end, you will see our solar neighborhood with entirely new eyes. How did this world get knocked on its side? What creates a magnetic field so chaotic it seems broken? We are about to peel back the layers of a true celestial mystery. What does it say about our universe that such strangeness exists right in our own cosmic backyard? Its strangest feature is the first thing you notice. Uranus does not spin upright like the other planets. It is tilted so far over, it essentially rolls around the sun like a cosmic ball bearing. While Earth leans at a gentle 23 degrees, Uranus is knocked almost completely on its side at a staggering 98-degree angle. For nearly a quarter of its 84-year orbit, one pole points directly at the sun, bathing it in constant daylight for 21 years, while the other pole is plunged into an equally long, frigid night. This is not a gentle wobble. This is the posture of a world that suffered a catastrophic event in its youth. The leading theory is a giant impact, a collision with an Earth-sized protoplanet that sent Uranus tumbling. But this simple story has problems. If such a massive object struck Uranus, the blow would have been so violent it should have vaporized the planet's atmosphere or left it scorching hot at its core. Yet Uranus is oddly cold, radiating very little internal heat. Even more puzzling, the entire family followed suit. Uranus's major moons and its delicate rings all orbit perfectly around its tilted equator, like a set of tiny disks spinning around the rim of a giant rolling wheel. This means the tilt happened early, before the moons fully formed from the debris of that same cataclysm. A single, shattering impact remains the best guess, but the evidence does not neatly line up. It suggests a violence so precise it knocked a world sideways while leaving its entire system in perfect, orderly alignment. What kind of collision could achieve that? The mystery of the tilted giant is our first clue that Uranus's history is written in a language of chaos we are only beginning to translate. This profound tilt may have frozen more than just its seasons. While Jupiter and Saturn glow with internal fire, radiating almost twice as much heat as they receive from the sun, Uranus is a different story. It is the solar system's coldest planet, a world in deep thermal slumber. Measurements show it emits barely any excess heat of its own, leaving its cloud tops at a bone-chilling -371 degrees Fahrenheit. For a gas giant, this is baffling. These planets are supposed to be engines of leftover energy, their massive interiors still contracting slowly under gravity, releasing heat that has been trapped since the solar system's birth. Uranus's engine appears to have stalled. One leading theory points back to that ancient cataclysm. Perhaps the colossal impact that knocked it sideways also blasted away much of its primordial heat, leaving its deep interior strangely quiescent. Another idea suggests its interior is not well mixed. Imagine a layered cocktail that never gets stirred. Uranus might have a stratified internal structure, with dense, icy material forming barriers that prevent heat from the core from rising smoothly to the surface. This would act like a planetary thermos, trapping the warmth deep within. Compare thermal images of the gas giants. Jupiter and Saturn blaze with the warmth of their own creation, their colorful bands fueled by powerful internal convection. Uranus, in stark contrast, shows only the faint, uniform chill of sunlight reflected back from a world that has gone thermally quiet. This missing heat is not just a curiosity. It directly shapes the planet's weather or lack thereof. Without a strong internal furnace to drive massive storm systems, Uranus's atmosphere appears deceptively calm and featureless from a distance, a serene blue mask over a deeply enigmatic and frozen heart. This profound chill seems to seep into every aspect of the planet, even its jewelry. Orbiting the tilted giant is a set of rings so dark and subtle they remained completely hidden from us until 1977. Unlike Saturn's brilliant, icy hoops that gleam in the sunlight, the rings of Uranus are narrow bands of what appears to be cosmic charcoal, absorbing almost all the light that touches them. Their discovery was itself a stroke of luck, astronomers watching as Uranus passed in front of a distant star, expecting the star to simply wink out. Instead, it flickered several times before and after the main event, revealing the silhouettes of these thin, dark barriers. We now know of 13 distinct rings, most no more than a few miles wide, composed of particles as dark as black velvet. What could they be made of? The leading suspicion points to organic compounds, complex carbon-rich molecules that have been baked and radiation darkened over billions of years, perhaps similar to the material found on some of our solar system's darkest asteroids. Their faintness raises a deeper question of origin. Most planetary rings are thought to be the shattered remains of moons, torn apart by a giant impact or ripped to pieces by the planet's gravity. But if that is the case for Uranus, why are these rings so narrow and orderly, and why is their material so uniformly dark? Some rings appear to be shepherded, their paths kept sharp and clear by the gravitational nudges of tiny, unseen moons orbiting just beside them. Yet confirming this from Earth is nearly impossible, these potential shepherd moons lost in the blinding glare of the planet itself. They are ghostly structures, these rings, elegant lines drawn in shadow around a world of secrets. Their darkness is not an absence but a statement, a clue that the story of the Uranian system is written in a substance far older and more mysterious than mere ice. That deep, frozen interior may be hiding a dynamo of pure chaos. Uranus possesses one of the most bizarre magnetic fields ever discovered. It is not centered on the planet's core, nor is it aligned with its poles. Instead, the field is wildly lopsided, its magnetic axis tilted at a staggering 59-degree angle from its rotational axis. To visualize this, imagine the magnetic North Pole of Earth being located somewhere in the middle of Canada. On Uranus, the magnetic North Pole is not even close to the geographic north. It is offset by nearly a third of the planet's radius, creating a field that is profoundly skewed. This means the magnetic field does not emerge symmetrically from a molten iron core like Earth's. The leading theory is far more exotic. Scientists believe the field is generated much closer to the surface, within a vast, slushy ocean of water, ammonia, and methane ices under extreme pressure and temperature. This is not ordinary water. It is a state called superionic water, where oxygen atoms are locked in a crystalline lattice while hydrogen ions flow freely through it, creating a highly electrically conductive soup. This layer churns and convects, acting as a planetary-scale electrical generator, but one that is messy, uneven, and far too close to the surface. The result is a magnetosphere that behaves like a broken compass spinning in a storm. As Uranus rotates, its off-kilter magnetic field tumbles through space, opening and closing dramatically with each 17-hour day. Solar wind particles do not stream smoothly around a protective bubble. They are funneled into this chaotic, lopsided field, creating a magnetosphere that might completely reconfigure itself on a daily basis. It is a protective shield that is perpetually off balance, a testament to the strange and turbulent forces churning just beneath that serene blue facade. That broken magnetic compass spins through the most extreme seasons in the solar system. Because Uranus rolls on its side, its poles take turns pointing directly at the sun for an unimaginable 21 years at a time. Picture a single summer day that lasts for 2 entire decades, followed by a night of equal, unbroken length. For 42 years, one hemisphere bakes in perpetual sunlight while the other freezes in absolute darkness. Logic suggests this should create a planet of violent extremes, with unimaginable storms raging at the boundary between the scorching day side and the frigid night side. Yet for a long time, Uranus appeared to be a calm, featureless blue marble, a world that seemed to sleep through its own dramatic solstices. This quiet defiance was a mystery in itself. Why wasn't the temperature difference between the sun-bathed pole and the dark pole driving planet wide weather chaos? The answer may lie in that profound internal cold. Without a strong internal heat source to stir the atmosphere, Uranus's weather systems are primarily driven by the weak sunlight it receives, which is almost 900 times fainter than what reaches Earth. The planet's deep, frigid interior acts like a vast thermal buffer, absorbing and redistributing solar energy with glacial slowness. The expected cataclysm of storms was muted, spread out over centuries instead of seasons. But Uranus had a surprise in store. When the planet approached its equinox in 2007, the moment when sunlight finally reached the equator after decades of polar summer, the Voyager 2 probe had long since passed by. It was Earth-based telescopes that watched in astonishment as massive storms, bright cloud systems the size of continents, erupted across the northern hemisphere. This was the planet's quiet period, the time it should have been most dormant. Instead, it was coming alive. These weren't the orderly bands of Jupiter, but giant, churning white caps of methane ice crystals punching through the upper atmosphere, driven by forces we still do not fully understand. A time lapse of a full Uranian year would show a world of eerie stillness, its blue face seemingly unchanging for decades, only to suddenly flare with unexpected and brilliant atmospheric fireworks at the precise moment we thought it would be at rest. The seasons here are not a cycle of gradual change, but a long, deep breath held for generations, finally released in a gasp of mysterious activity. The serene blue face of Uranus finally revealed a storm of its own. In 2006, the Hubble Space Telescope captured something startling, a dark vortex swirling in the northern hemisphere of this supposedly placid world. It was the first dark spot ever seen on Uranus, a massive, high-pressure storm akin to Jupiter's Great Red Spot, but far more elusive and mysterious. This was not a bright cloud of methane ice, but a deep, brooding hole in the upper atmosphere, a gap through which we could peer into the planet's darker, warmer layers below. Scientists believe the spot is a giant anticyclone, a vortex where atmospheric gases are sinking rather than rising, and its dark coloration hints at a startling composition, potentially rich in hydrogen sulfide, the same gas that gives rotten eggs their distinctive smell. The very existence of such a storm was a shock, challenging the long-held view of Uranus as a meteorologically dead world, but its mystery deepened with its behavior. Unlike Jupiter's centuries-old Great Red Spot, the dark spot on Uranus proved transient. By 2011, just 5 years after its discovery, follow-up Hubble observations showed it had completely vanished. This fleeting nature is the core of the enigma. What forces suddenly conspire to birth a storm system thousands of miles across on a planet with such weak internal heat? And what causes it to dissipate just as abruptly, leaving no trace? The leading theory suggests these dark vortices may be rooted deep in the water ammonia ocean beneath the clouds, occasionally punching through the upper atmosphere like a colossal, slow-motion geyser before being sheared apart by winds or smoothed over by unknown atmospheric processes. They are ghosts in the machine, appearing without warning on the blue canvas, a brief signature of the turbulent forces we cannot see, only to fade back into the planet's deep and secretive silence. These fleeting storms are just surface ripples over a truly alien sea. Beneath the serene blue clouds of Uranus lies not a rocky core like Earth's, but something far more fantastical, a vast and churning ocean. Yet this is no ocean of liquid water as we know it. The immense pressure and heat thousands of miles down transform familiar molecules into an exotic, superionic state. Picture a substance that is both a solid and a liquid at the same time. In superionic water, oxygen atoms are locked into a rigid crystalline lattice, like the structure of ice, but hydrogen ions break free and flow freely through this solid framework like a liquid. It is essentially a conductive ice, a material that can carry electric currents while remaining under crushing planetary pressure. This is the hypothesized engine room of Uranus, a slushy, electrically conductive layer of water mixed with ammonia and methane that may extend for thousands of miles, making up the bulk of the planet's interior. We call Uranus an ice giant, but that label is deeply misleading. The ice here is not cold but searingly hot, and it is not solid in any normal sense. It is a bizarre fourth state of matter that exists only in the most extreme laboratories on Earth and in the hearts of distant worlds. The exact recipe of this deep ocean remains one of the planet's greatest secrets. What is the ratio of water to ammonia to methane? How does this mixture churn and convect? Does it have distinct layers, or is it a uniform, exotic soup? Each possibility paints a different picture of the planet's formation and its internal dynamo. This superionic layer is the leading suspect for generating Uranus's lopsided and chaotic magnetic field. As this conductive material slowly swirls and churns, it acts like a gargantuan, messy electrical generator, but one buried closer to the surface than the core. The field it produces is therefore off-center and tilted, a direct reflection of the turbulent, unconventional fluid dynamics happening within. The chemistry in such a place is beyond exotic. Under those pressures and temperatures, normal compounds break down and reform into substances we can scarcely imagine, perhaps even raining diamonds or forming crystalline ammonia compounds that behave like metals. This hidden ocean is not a placid reservoir, it is a cauldron of extreme physics, a realm where the very rules of matter are rewritten, and its mysterious currents silently dictate the strange behavior of the world above. Orbiting this world of hidden oceans are 5 strange satellites, each with a story etched into its frozen crust. The major moons of Uranus, Miranda, Ariel, Umbriel, Teutonia, and Oberon present a gallery of cosmic puzzles. Their very existence begs a foundational question. Were they born alongside their planet from a swirling disk of gas and dust, or are they celestial wanderers captured by Uranus's gravity long after its formation? The varied and violent geology we see argues for a dramatic hybrid history. Take Miranda, the innermost of the 5. Voyager 2's images revealed a world that looks as if it was shattered and clumsily glued back together. Its surface is a chaotic jigsaw puzzle of giant fault canyons, some 12 times deeper than the Grand Canyon, and bizarre, wedge-shaped regions called coronae. One of these, a striking chevron pattern, resembles a colossal celestial racetrack stamped into the ice. This is not the gentle terrain of a quietly cooling world. Miranda's tortured face screams of a cataclysmic past, likely a series of shattering impacts that broke the moon apart, only for its pieces to reassemble under their own gravity into a Frankenstein's monster of a world. Such violence hints that the early Uranian system was a demolition derby, with moons constantly colliding, fragmenting, and reforming. Yet not all the moons show such obvious trauma. Ariel appears the youngest, with bright, fresh surfaces and vast networks of sinuous valleys that may have been carved by flowing ammonia water ice in the distant past. Umbriel, in stark contrast, is ancient and dark, its face heavily cratered and seemingly unchanged for eons, a silent witness to that primordial chaos. The 2 largest, Teutonia and Oberon, show hints of their own tectonic activity, with enormous rift valleys suggesting they may have expanded as their interiors froze long ago. This wild diversity suggests a complex origin story, perhaps a mix of formation from an accretion disk and the later capture of stray objects, all followed by an epoch of relentless bombardment. But the greatest secret these moons may hold is not on their surfaces but deep within. the gravitational tugging from Uranus and their sibling moons generates internal heat through tidal forces. For some, like Ariel or even Miranda, this could be enough to maintain a layer of liquid water, a subsurface ocean, sandwiched between a frozen crust and a rocky core. These hidden seas, if they exist, would be places of profound darkness and pressure, yet they represent the most tantalizing possibility of all, that within the retinue of this frozen, tilted giant, there might be pockets where the chemistry for life could, against all odds, quietly stir. Miranda stands alone as the strangest world Voyager 2 ever saw. This tiny moon, just 290 miles across, presents a landscape of such violent contradiction it defies simple explanation. Its surface is a chaotic patchwork, a jigsaw puzzle assembled from pieces that do not belong together. Towering cliffs soar 12 miles high, making its Verona Rupes the tallest known cliff face in the solar system. Vast trapezoidal regions of grooved and ridged terrain, called coronae, look like giant celestial racetracks or abstract art stamped into the ice. One of these, named Inverness Corona, resembles a colossal chevron pattern, while another, Arden Corona, is marked by concentric ridges and troughs. These features sit abruptly beside older, heavily cratered terrain, as if three different moons were smashed together into one. The leading theory to explain this Frankenstein's appearance is as dramatic as the moon itself. Scientists believe Miranda was likely shattered in a series of gargantuan impacts early in its history, broken into pieces that then slowly recoalesced under their own weak gravity. This process of violent disruption and haphazard reassembly would explain the bizarre juxtaposition of terrains, with denser core material rising to form the coronae while older crustal fragments settled back into place at odd angles. It is a world literally put back together wrong. An alternative theory points to Uranus itself. The planet's immense gravity, combined with Miranda's eccentric orbit, could have created intense tidal heating in the moon's past. This internal friction might have partially melted its interior, driving massive plumes of warm ice upward to deform the crust into those strange, ovoid patterns before everything froze solid once more. The truth may be a combination of both, a history of being torn apart and stitched back together, then stretched and kneaded by tidal forces. The detailed mosaics sent back by Voyager 2 remain our only close-up look, and they show a world of stunning, unsettling beauty. Miranda is not a dead moon. It is a geological document of pure chaos, a permanent record of a childhood so traumatic it left a world scarred and unique for all time. Miranda's fractured beauty is a monument to violence we have only glimpsed from a distance. The single set of close-up images we possess of Uranus and its moons came from a fleeting visitor, a spacecraft that passed by nearly 4 decades ago. Voyager 2's flyby in 1986 remains the only time humanity has ever looked upon this system up close. Every detailed map, every theory about dark rings and tilted fields, every haunting image of Miranda's cliffs stems from a few precious hours of data gathered as the probe raced past at 42,000 miles per hour. Since that brief encounter, Uranus has been studied only from across a gulf of billions of miles, a pale blue dot in our most powerful telescopes. This creates a profound and puzzling gap in our exploration. Why, in all the years since, have we not returned? The mystery is not one of science but of priority. Sending a dedicated orbiter to Uranus is a monumental undertaking. The journey alone, even with gravity assists from Jupiter, would take 12 to 15 years. Such a mission requires a rare alignment of political will, sustained funding over decades, and a launch window that occurs only once every generation. Competing visions for exploration, from Mars rovers to lunar bases, often draw focus and resources closer to home. The technical challenge is immense. A spacecraft must carry enough power and fuel to survive the long, cold voyage, and then perform a critical orbital insertion maneuver around a planet with such weak gravity. all while operating on sunlight 900 times fainter than at Earth. It is a test of patience and engineering on a scale we seldom attempt, yet what we could learn makes the endeavor irresistible. A modern Uranus orbiter, equipped with instruments far beyond Voyager's era, could peer into the planet's hidden layers. It could precisely measure the gravitational field to map the structure of that superionic ocean, analyze the composition of the dark rings particle by particle, and monitor the atmosphere through an entire season to unravel the logic behind its sudden storms. A probe descending into the blue haze could taste the air directly, determining the exact mix of hydrogen, helium, and that suspected hint of rotten egg gas, hydrogen sulfide, finally confirming what the upper clouds are made of. It could fly among the major moons, mapping their hidden subsurface oceans with ice-penetrating radar and searching for recent geologic activity. Proposed missions like the Uranus orbiter and probe concept studied by NASA envision a flagship spacecraft that would become a permanent sentinel in the Uranian system. Picture this new explorer, a craft with a large communications dish pointed home and vast solar panels to catch the dim sunlight, deploying a sturdy atmospheric probe that would blaze a trail of fire into the unknown blue. For over 30 years, this world has been a collection of unanswered questions and tantalizing, low-resolution hints. Returning is not merely a follow-up visit, it is the only way to transform those mysteries into understanding. The greatest enigma surrounding Uranus may not be on its surface, but in our own reluctance to make the long journey back. That serene blue face hides a profound imbalance. Uranus's atmosphere is not the uniform, featureless haze it first appears to be. When viewed in enhanced colors that reveal subtle contrasts, a surprising structure emerges, faint bands of clouds and hazes that circle the planet. Yet these bands are not distributed evenly. The atmosphere of Uranus is strikingly asymmetric, with one hemisphere often appearing more active and banded than the other. This lopsidedness is another fingerprint of its extreme tilt and weak internal heat. Without a strong central engine to drive global circulation, the atmosphere seems to respond sluggishly and unevenly to the feeble sunlight, creating weather patterns that favor one side of the world for reasons we do not yet fully grasp. High-altitude clouds of methane ice do occasionally erupt brilliant white features that stand out against the blue, but they tend to cluster in specific regions rather than forming the orderly, planet-encircling belts we see on Jupiter or Saturn. The contrast with its sibling Neptune is particularly puzzling. Both are ice giants similar in size and composition, yet Neptune blazes with dynamic, churning dark spots and bright, fast-moving cloud bands. Uranus, by comparison, often seems meteorologically subdued, its features slower to form and fainter to our eyes. Why would two such similar worlds behave so differently? The answer likely lies deep within, in that missing internal heat. Neptune radiates about 2.6 times more energy than it receives from the Sun, fueling a turbulent atmospheric engine. Uranus, radiating almost no excess heat, must rely almost entirely on sunlight, which at its distance is little more than a dim candle. Its atmosphere is thus a system running on a near-dead battery, stirring with a slow, asymmetric languor that we struggle to decode. Deeper down, where pressures mount to millions of times that of Earth's surface, the atmosphere undergoes transformations straight out of myth. Scientists theorize that methane, the gas that gives Uranus its blue hue, breaks apart under the incredible pressure. The carbon atoms, freed from their bonds, are squeezed into crystalline structures, falling in a perpetual glittering shower of diamond rain towards the hidden core. This is not mere speculation. Laboratory experiments have recreated the extreme conditions and watched synthetic diamonds form. On Uranus, this process could be constant, with hailstones of solid diamond sinking through slushy layers of ionic water. It is a world where the sky might literally rain jewels, a hidden, fantastical process that contributes to the planet's overall thermal weirdness by locking heat away in its deep interior. So while the upper clouds may appear quiet and lopsided, below them rages a slow-motion drama of elemental alchemy where common gases are forged into precious stones in the eternal dark. Even the planet's silence speaks in a strange tongue. Uranus broadcasts a faint, cryptic signal into the void, a whisper of radio waves that holds clues to its turbulent heart. These are not deliberate transmissions, of course, but natural emissions generated as the solar wind, that stream of charged particles from the sun, slams into the planet's lopsided and tumbling magnetic field. The interaction creates bursts of energy that ripple out as radio waves, a signature of the magnetosphere's chaotic dance. For scientists, tuning into this cosmic static is like listening to the heartbeat of a hidden machine. The mystery lies in the signal's irregular, unpredictable nature. Unlike the steady pulsing of Jupiter's powerful radio emissions, which are tightly locked to the planet's rotation, the signals from Uranus are weak, broken, and seem to stutter. They come in bursts that do not follow a clear rhythm, a direct consequence of that profoundly tilted and offset magnetic field. As Uranus spins, its magnetosphere doesn't sweep through space like a steady lighthouse beam. It wobbles and lurches, opening and closing to the solar wind in a complex, uneven pattern. This creates a radio voice that is sporadic and hard to decipher. When these radio waves are converted into sound we can hear, the result is eerie. The emissions become a series of pops, crackles, and descending whistles, like distant lightning or static from a broken radio receiver tuned between stations. It is the sound of a protective shield under immense and uneven stress. Listening to these sounds is more than a novelty, it is a diagnostic tool. The specific frequencies and patterns of the emissions are shaped by the environment that generates them, particularly the density and motion of charged particles within the magnetosphere. By decoding this irregular radio chatter, scientists hope to map the invisible structure of Uranus's magnetic field in far greater detail than Voyager 2's brief snapshot allowed. More importantly, the radio waves act as a probe into the planet's deep interior. They are a direct product of the motions within that conductive superionic ocean. The irregularities in the signal may reflect turbulence, currents, or uneven flows in that hidden layer. A future orbiter listening intently to this radio whisper could, in effect, perform an ultrasound of the planet, using the bursts of static to chart the churning depths of an ocean we will never see. This faint broadcast from the edge of our solar system is a continuous, if baffling, data stream, a real-time report from a realm of extreme physics, and we are only just learning how to listen. The faint radio whispers fade into a deeper silence, one held in place by tiny, unseen sentinels. Among Uranus's dark rings, a delicate gravitational ballet maintains order, performed by moons so small they are barely more than mountains in space. Take the Epsilon ring, the brightest and most distinct of the set. It is a narrow ribbon of dark material, only a few dozen miles wide, yet it maintains a sharp, defined edge against the void. This precision is not an accident. It is enforced. On either side of this ring orbit two tiny moons, Cordelia and Ophelia, acting as gravitational shepherds. Their minuscule but persistent tugs on the ring particles create a celestial fence. A particle drifting inward toward the planet will feel Cordelia's pull, nudging it back outward. One drifting outward will be tugged back inward by Ophelia. This constant, gentle herding keeps the ring particles confined to a narrow track, preventing them from spreading out into a diffuse haze over millions of years. It is a perfect clockwork system of checks and balances, yet this elegant solution presents its own profound mysteries. Are Cordelia and Ophelia the only shepherds? The other narrow rings suggest similar guardians, but these moons, if they exist, are too faint and small to have been seen from Earth or even clearly by Voyager. They are gravitational ghosts, inferred but not yet seen, hiding in the glare of the planet. Their very existence raises a deeper question of origin. How did such small moons form in these exquisitely precise orbits, perfectly positioned to corral the rings? Did they coalesce from the same debris that formed the rings, or are they captured asteroids that somehow migrated into this perfect, balanced arrangement? The system is a masterpiece of orbital mechanics, but it is also incredibly fragile. A passing comet or a collision between moons could disrupt this balance, potentially causing a ring to collapse or scatter within a surprisingly short cosmic timescale. The fact that we see these sharp rings today means this delicate dance has been maintained for eons, a testament to a quiet, persistent order imposed upon the dark debris of the Uranian system. What other tiny wardens might be orbiting there, unseen, maintaining the shadows we call rings? The quiet blue mask of Uranus conceals a raging atmospheric beast. For a world so profoundly cold and seemingly dormant, it possesses one of the most startling contradictions in our solar system: winds that scream across its cloud tops at speeds exceeding 560 miles per hour. These are not the gentle breezes of a placid giant, but gales that dwarf the most powerful hurricanes Earth can muster. The mystery is not their presence, but their origin. What unseen engine could possibly whip the atmosphere of such a thermally dead world into such a frenzy? On Jupiter and Saturn, colossal storms are fueled by powerful internal heat rising from their deep, hot interiors. On Neptune, which also boasts supersonic winds, a strong internal furnace provides the necessary energy. Uranus, radiating almost no excess heat of its own, lacks this obvious driver. Its winds must be powered almost entirely by the faint, distant sun, a candle trying to stir a global ocean. This presents a profound puzzle in planetary physics. One theory suggests the answer lies in the very depth and uniformity of the atmosphere. With little internal heat to create rising and falling columns of gas, the winds on Uranus might be remarkably shallow, confined to a thin, high-speed jet stream in the uppermost cloud layers. Another idea points to the planet's extreme tilt and the resulting 42-year seasons. The slow, massive transfer of solar energy from the sunlit hemisphere to the dark one over decades could set up colossal pressure differences, driving these high-altitude winds in a planet-wide circulation pattern we are only beginning to model. Visualize a graphic comparing wind speeds across the solar system. Saturn's jet streams might top out at over 1,000 miles per hour, but they are fueled by a roaring internal dynamo. Neptune's dark spots race along at similar speeds to Uranus, backed by its own strong heat flow. Uranus sits alone on this chart, a world with the atmospheric ferocity of its siblings, but powered by a source of energy so faint it verges on the impossible. Its winds are a ghost in the machine, a violent symptom of a planetary system running on a logic we have yet to fully comprehend. Even its signature color is not a constant. Uranus undergoes a subtle but real transformation in hue over the course of its epic year, shifting between shades of pale blue and a slightly greener cyan. This is not a trick of the light or an illusion, but a measurable change observed by powerful telescopes like Hubble over decades. When the planet is at solstice with one pole pointed directly at the sun, it tends to appear a touch greener. As it approaches equinox with sunlight falling more evenly on its equator, it becomes a more uniform, brighter blue. Time-lapse compilations of Uranus across the years tell this story in slow motion, a world slowly changing its tint over a human lifetime. The cause is a complex atmospheric ballet. The dominant blue comes from methane gas in the upper atmosphere, which absorbs the red wavelengths of sunlight and reflects the blue back into space. The greenish tinge is believed to come from a thinner layer of methane ice haze, a high-altitude smog of tiny frozen particles. The mystery is in the timing and distribution of this haze. During the long polar summer, increased sunlight reaching the pole might trigger the formation of more of these methane ice crystals, creating a thicker haze that lends a greener cast to that hemisphere. At equinox, when sunlight is more evenly distributed, this haze may thin out or be distributed differently, allowing the deeper blue of the methane gas below to dominate. But the exact chemical and physical processes are still unclear. What controls the formation and dissipation of this high-altitude smog? How do Uranus's sluggish winds transport these particles from the sunlit pole to the dark one? The color change is a visible symptom of the planet's slow, deep atmospheric breathing, a 42-year cycle of photochemistry and circulation that we are only beginning to decode. It is a reminder that even a world that seems static from our brief perspective is engaged in a perpetual, graceful, and mysterious dance of light and chemistry. The faint radio whispers and delicate ring shepherds hint at a system far more crowded than we can see. Beyond the 5 major moons and the handful of tiny shepherds we have spotted, Uranus may be host to an entire hidden population, a celestial archipelago of undiscovered mini-moons. These would be dark, icy bodies, perhaps only a few miles across, orbiting within the ring system itself or in distant, lonely paths far from the planet. Their existence is more than just speculation. It is a gravitational necessity. Certain subtle features in the rings, slight kinks or gentle waves, cannot be fully explained by the gravity of the moons we already know. These anomalies are like footprints in the dust, suggesting the presence of unseen masses, their gentle tugs sculpting the fine structure of the rings from the shadows. Detecting these moonlets from Earth, however, is a monumental challenge. At its closest, Uranus is still over 1.5 billion miles away. Against the overwhelming glare of the planet itself, a tiny, dark object reflecting almost no sunlight is virtually invisible to our most powerful telescopes. It is like trying to spot a single black pebble on a distant, sunlit beach while staring directly into a brilliant blue spotlight. The Voyager 2 flyby gave us our best chance, but its cameras were designed for a broader survey, not a meticulous hunt for such faint, small dots in the vastness. Future missions equipped with sensitive modern cameras and dedicated observation time could revolutionize our census of the Uranian system. Imagine an orbiter performing a systematic scan, its instruments shielded from the planet's glare, slowly revealing a whole new celestial neighborhood. Artist impressions help us visualize the scene, a dark, lumpy moonlet, its surface pitted and ancient, orbiting silently within a narrow gap in the charcoal rings, its gravity clearing a path and shepherding the particles on either side into sharp, defined edges. We might find families of these objects, remnants of the violent collisions that shaped the system's early days, or solitary wanderers captured from the Kuiper belt. Each discovery would be a key, helping to unlock the precise gravitational equations that maintain the strange, dark jewelry of this tilted giant. The rings are not just decorations, they are a dynamic clockwork, and every missing gear, every hidden moon holds a piece of the story. The very air of Uranus holds a thermal paradox. While its cloud tops shiver at hundreds of degrees below zero, the outermost fringe of its atmosphere, a wispy layer called the exosphere, is scorching hot, reaching temperatures of over 900 degrees Fahrenheit. This is not a gentle warmth, but a heat that defies all common sense. The sun, nearly 2 billion miles away, is far too weak to provide such intense heating. So where is the fire? The answer lies in energy, but not from sunlight. One leading suspect is the solar wind. As that stream of charged particles from the sun slams into Uranus's chaotic magnetic field, it can transfer tremendous energy to the sparse atoms in the upper atmosphere, making them vibrate faster, which we measure as heat. Another possibility involves auroras. On Earth, the northern lights are a beautiful side effect of solar particles interacting with our magnetic field. On Uranus, with its wildly tilted magnetosphere, auroral processes could be far more energetic and widespread, acting like invisible heating coils in the polar sky. A third, more subtle theory points to gravity waves. These are not the ripples in space-time, but vast, slow-moving undulations in the atmosphere itself, like waves on an ocean. As these waves travel upward from the dense lower atmosphere and break in the thin exosphere, They could dump their energy like a silent, planet-wide crash of surf, generating intense heat. This mystery is not unique to Uranus. Jupiter and Saturn also have surprisingly hot exospheres, and even Earth's upper atmosphere is hotter than scientists once expected. But Uranus, with its profound cold below and its lack of internal heat, makes the contrast especially stark. A diagram of its atmospheric layers would show a steep temperature plunge through the clouds, followed by a sudden and dramatic spike in the outermost, most tenuous region. It is a world wrapped in an invisible, blistering cloak, a feverish halo around a frozen heart. The source of that fever remains one of the most active puzzles in planetary science, a reminder that even the emptiest seeming spaces can hold reservoirs of furious, hidden energy. That blistering exosphere is the stage for a light show that defies all earthly logic. The auroras of Uranus are unlike anything witnessed on our own planet. On Earth, the northern and southern lights are majestic curtains of color, dancing in neat rings around the magnetic poles. On Uranus, with its magnetic axis tilted almost 60 degrees from its rotational axis, the concept of a pole loses all meaning. The auroras here are not anchored to the geographic north or south. Instead, they appear as faint, glowing smudges scattered across the planet, flickering in unexpected places, sometimes even near the equator. They are the ghostly signature of a broken compass. The Hubble Space Telescope first captured these elusive lights in ultraviolet light, revealing them not as vivid green ribbons, but as diffuse, patchy glows that come and go with the planet's chaotic rotation. Their very detection was a triumph, as they are incredibly faint, washed out by the sunlight reflecting off the blue cloud tops below. The mystery of these auroras goes beyond their strange location. An aurora is born when charged particles, typically from the solar wind, are channeled by a planet's magnetic field and slam into its upper atmosphere, causing the gases there to glow. On Uranus, the process is profoundly muddled. The planet's off-center, tumbling magnetic field creates a magnetosphere that is constantly in flux, opening and closing like a lopsided umbrella with each 17-hour day. This means the streams of charged particles do not follow a reliable path. They are funneled into this chaotic field, striking the atmosphere in a scattershot pattern wherever the magnetic geometry allows at that particular moment. The result is an auroral display that lacks a permanent home, a will-o'-the-wisp that flickers across the blue face of the giant. But an even deeper puzzle remains: what exactly are these particles hitting? Earth's brilliant auroras are powered by solar particles exciting oxygen and nitrogen. Uranus's atmosphere is dominated by hydrogen and helium, with that suspected layer of hydrogen sulfide far below. The faint, ultraviolet glow suggests the solar particles are exciting molecular hydrogen, a process that produces a much dimmer light. Yet the exact chemistry of these high-altitude collisions, in an atmosphere so cold and dominated by such simple ingredients, is still a map of unknown. Looking at those Hubble images, you see not a spectacle, but a clue, a faint, ultraviolet fingerprint left by invisible particles spiraling along invisible and wildly skewed field lines. It is a light show for no one, a silent, scattered fireworks display in the near vacuum, illuminating the profound and ongoing disarray deep within the planet's hidden heart. This profound darkness is a chemical signature. The rings of Uranus are not just faint, they are composed of some of the blackest material in the solar system, absorbing over 99% of the light that strikes them. This is not simple dust or dirty ice. It is a substance with a deliberate, engineered-seeming gloom, and its identity is a direct clue to the system's violent past. Spectroscopy, the technique of breaking light into a rainbow to reveal chemical fingerprints, offers our best hints. When scientists point telescopes at the rings, the reflected light spectrum is nearly flat, devoid of the sharp dips and peaks that would indicate water ice or simple minerals. It is the spectral signature of something ancient and complex. The prime suspects are radiation-darkened organics, thick tarry compounds rich in carbon, similar to the material found on some of the darkest asteroids and cometary nuclei. Imagine taking simple ices and methane, bombarding them for billions of years with relentless ultraviolet light from the sun and punishing cosmic rays. This radiation cooks and polymerizes the material, stripping away hydrogen and linking carbon atoms into long, complex chains, creating a dark, carbonaceous sludge. Another candidate is graphite, a form of pure carbon, or even more exotic carbon compounds we have yet to name. The mystery deepens when we ask why this material remains so pure. In other ring systems, like Saturn's, constant micrometeorite impacts kick up brighter water ice dust that settles on ring particles, giving them a fresher, brighter look. Around Uranus, this process seems to have failed. One possibility is that the ring particles themselves are incredibly porous, like cosmic charcoal briquettes, so any bright icy dust that lands on them simply sinks into the dark matrix, vanishing from view. Another, more dramatic idea is that the rings are simply too young to have been coated, or that some ongoing process actively removes bright material. Artist concepts based on spectral data visualize these rings not as glittering hoops, but as a collection of countless mountain-sized chunks of what looks like coal or asphalt, tumbling in silent, precise orbits. Their profound darkness is not an absence but a preservation. They are a time capsule holding a sample of the primordial, carbon-rich gunk that swirled around the infant Uranus, material that was never incorporated into the planet or its moon. By decoding the exact recipe of this cosmic charcoal, we could read the very ingredients list from the dawn of the ice giants, understanding the chemical conditions that built one of our solar system's strangest worlds. That profound darkness may not be evenly distributed. The rings we see appear as smooth, continuous loops, but what if they are not? Around Neptune, astronomers discovered something remarkable. Its faint rings are not complete circles, but clumpy arcs, bright segments that look like broken pieces of a necklace. This discovery forces a tantalizing question for its sibling. Could Uranus, with its own set of dark, narrow rings, also harbor hidden arcs? These would not be the broad, uniform bands we have charted, but dense, localized clumps of material, concentrations of that charcoal dark rubble bunched together in specific regions of an orbit. Finding them would require looking in a new way, searching for subtle variations in brightness along the thin, dark lines we think we know. The very existence of such arcs presents a dynamical puzzle. In the orbital mechanics of rings, everything should spread out. Collisions between particles, the gentle pressure of sunlight, even gravitational nudges should cause any clump to dissipate into a smooth, uniform ring over a relatively short time. For arcs to persist for millions of years, something must be actively confining them, acting like a celestial shepherd for a specific flock. The leading theory is resonant confinement by a moon. Imagine a tiny moon orbiting just inside or outside the ring. As the ring particles travel around Uranus, they periodically catch up to the moon's gravity at the same point in their orbits, experiencing a consistent, repeating tug. This gravitational resonance can create stable zones like safe harbors in a sea of motion, where particles are herded together and prevented from drifting away. A single moon could theoretically shepherd multiple arcs, its gravity creating a series of stable pockets along the ring's path. We have seen this dance elsewhere. Saturn's G-ring is maintained by the moon mimas, and Neptune's famous ring arcs are likely confined by the gravitational influence of the small moon Galatea. For Uranus, the potential shepherds are already suspected. Those unseen moonlets we believe are sculpting the sharp edges of the rings. Could one of these gravitational ghosts also be creating hidden density variations, clumping the dark material into arcs we have simply not yet resolved? Future observations with next-generation telescopes, like the James Webb Space Telescope or a dedicated Uranus orbiter, might finally answer this by staring intently at each narrow ring, measuring the faintest flickers in their darkness. We could map their true structure. The discovery of arcs would be more than a new feature. It would be a direct window into the gravitational symphony of the entire system, revealing the precise orbits and masses of moons we have never seen. The smooth rings we perceive may be an illusion, a simplification of a far more intricate and cluttered reality hiding in plain sight. Its signature blue-green hue is a chemical question mark. That distinctive color comes from methane gas high in the atmosphere, a layer that acts like a celestial filter, soaking up the red sunlight and reflecting the blue back into space. But this simple fact opens a deeper mystery. Where did all this methane come from? For a planet so distant and cold, its very atmosphere holds a clue to its formation. Methane should not be this abundant so far from the sun. In the primordial cloud that birthed our solar system, temperatures were too warm at Uranus's orbit for methane ice to condense and stick to the growing planetesimals. So how did Uranus acquire such a rich envelope of it? There are three leading possibilities, each pointing to a different origin story. First, it could be primordial, meaning it was part of the original mix of gas and dust that collapsed to form the planet itself, somehow trapped despite the heat. Second, it could have been outgassed from the planet's deep interior, released from that slushy superionic ocean or from icy materials that melted and rose to the surface over eons. Third, it could have been delivered later by a relentless bombardment of methane-rich comets from the outer solar system, a slow cosmic rain that painted the world blue. The answer matters because it tells us what Uranus is made of at its core. If the methane is mostly primordial, it suggests the planet formed quickly, capturing a thick atmosphere before the young sun's radiation could blow the lighter gases away. If it was outgassed, it implies a more chemically active and differentiated interior, with layers that have been churning and releasing volatiles for billions of years. And if it was delivered by comets, it paints a picture of a violent, chaotic youth where the planet's character was shaped by countless impacts. This mystery is tied to another puzzle, the absence of other expected gases. Why is methane so prominent while other, heavier hydrogen compounds seem scarce? The upper atmosphere may hold another clue, a suspected trace of hydrogen sulfide, the gas that smells of rotten eggs. Detecting it definitively is incredibly difficult from Earth, but its presence or absence would rewrite the chemical recipe of the planet's birth. Deeper down where pressures mount, the methane does not stay as a gas. It condenses into clouds, forming layers of methane ice crystals that create the planet's occasional bright, high-altitude features. Imagine a graphic showing an absorption spectrum, the rainbow of sunlight reflected from Uranus. You would see deep, sharp black lines where methane has greedily absorbed specific colors of light, a barcode of its presence. Yet that barcode is incomplete, missing the signatures of other molecules we might expect to see. This missing data is a silent testament to the unique conditions that forged this world. The methane is more than a color, it is a messenger from the past, and we are still learning how to read its story. The dynamo powering this broken magnetic field is unlike any other in our solar system. While Earth's field is born in the churning of molten iron at its core, and Jupiter's from metallic hydrogen deep within, the magnetic heart of Uranus is thought to lie in a slippery, exotic ocean. This is the superionic layer, a shell of water and ammonia under such immense pressure and heat that it behaves as both a solid and a liquid. Within this thick, global ocean, oxygen atoms are locked into a rigid crystalline lattice, a solid scaffold. But the hydrogen ions break free, flowing through that lattice like a charged fluid. This creates a highly electrically conductive soup, a perfect medium for generating a planetary magnetic field through its slow, convective motions. The dynamo, therefore, is not buried at the planet's deep center. Instead, it operates in this relatively thin, shell-like layer much closer to the surface. This shallow, off-center location is the key to explaining the magnetic field's profound tilt and offset. A dynamo in a spherical core tends to produce a neat, aligned field, like a bar magnet through the planet's center. But a dynamo operating in a thick, uneven shell can generate a field that is messy, lopsided, and tilted, exactly as we observe. The fluid dynamics here are extraordinarily difficult to model. This is not a simple liquid like water in a pot. The superionic material is viscous and strange, its flow patterns dictated by the complex interplay of temperature, pressure, and composition across thousands of miles. Scientists must simulate how this slushy, conductive layer churns and convects, how heat might rise in plumes from below, and how the rotation of the planet shears these motions into the organized chaos needed to sustain a magnetic field. Visualize a cutaway of the planet. From the outside in, you see the blue cloud tops, then deep layers of hydrogen and helium. But beneath that, instead of a small, rocky core, you encounter this vast, glowing orange shell, the superionic ocean. Within it, swirling lines of force represent the convective currents, their motion twisted by the planet's spin. The magnetic field lines depicted in blue erupt not from the center, but from within this shell, emerging at a wild angle. Modeling this is a frontier of computational physics. Each simulation requires balancing equations for fluid motion, thermodynamics, and electromagnetism in an environment we can never visit. Small changes in the assumed thickness of the shell or the amount of ammonia mixed into the water can produce radically different magnetic fields in the models. The goal is to find the precise recipe that replicates the single, strange snapshot Voyager 2 took almost 40 years ago. This layer is more than a scientific curiosity. It is a new state of planetary matter in action. Understanding its slippery, conductive dance is the only way to decode the true nature of the force field that wraps this tilted giant in its chaotic, protective embrace. That chaotic magnetic heart beats beneath a sky of deceptive serenity. Uranus presents us with a profound atmospheric paradox, a world of screaming winds and extreme seasons that often wears the face of a perfectly calm, featureless aquamarine marble. This is the quiet weather mystery. How can a planet with such violent ingredients produce such a bland exterior? The contrast with its sibling Neptune is startling. Place their images side by side. Neptune is a study in turbulent beauty, streaked with bright white methane clouds and dominated by great dark storms like the famous Great Dark Spot, a world that looks perpetually caught in a celestial hurricane. Uranus, in the same family portrait, often appears as a smooth, uniform disk of pale blue, a serene pool of color floating in the black. Both are ice giants, similar in size, composition, and distance from the Sun. Yet one is a meteorological drama, the other a study in stillness. The answer likely lies in that missing internal heat. Neptune radiates a significant amount of its own warmth from within, acting as a powerful engine that drives convection, churning the atmosphere into the complex cloud patterns and massive storms we see. Uranus, with its deep internal cold, lacks this central furnace. Its atmosphere is primarily driven by the feeble sunlight it receives, a candle trying to heat a cathedral. Without a strong heat source rising from below to punch through the atmospheric layers, large-scale storm formation is suppressed. The energy input is too weak and too diffuse to organize the chaos we associate with gas giants. Another theory points to a thermal lag of staggering proportions. The 42-year seasons on Uranus are so long that the atmosphere may take decades, even centuries, to fully respond to the shifting solar energy. The planet's deep, frigid interior acts as a massive thermal buffer, absorbing and redistributing heat with glacial slowness. A sudden burst of sunlight at the pole does not immediately trigger a planet-wide storm. It is slowly digested over an epoch, resulting in that eerily calm facade. There may also be a layered, stable structure to the atmosphere itself. Imagine a thick blanket of haze, a global smog of methane and other hydrocarbons sitting atop the weather layer. This could act as a lid, smoothing out and obscuring the turbulent activity happening in the clouds below. The few storms that do punch through, like the fleeting dark spot, might be rare exceptions that briefly breach this tranquil ceiling. So the quiet is not an absence of motion, but a symptom of a system running in slow motion on a near-dead battery. The fast winds are there, but they may be confined to thin, high-altitude jets, unable to organize into the visible, planet-spanning storms we expect. Looking at that serene blue ball, we are not seeing a dead world, but a deeply sluggish one. A giant whose atmospheric heartbeat is so slow and deep we can barely perceive its pulse across the brief window of a human lifetime. The profound quiet of Uranus may hide a secret not on the planet, but in its retinue. Within the frozen crusts of its largest moons, particularly Titania and Oberon, there exists a tantalizing possibility, a hidden ocean. It is a concept that shifts the search for life from the inhospitable cloud tops to the dark, pressurized depths of a distant, icy world. These moons are not barren rocks, but complex geological bodies, and their interiors may be warm enough to maintain liquid water, the one indispensable ingredient for life as we know it. The energy for this warmth does not come from the distant sun, but from two relentless internal forces, tidal heating and radioactive decay. As these moons orbit Uranus, the planet's immense gravity constantly flexes and stretches their interiors, generating friction and heat, much like repeatedly bending a metal paperclip until it becomes warm. This process, tidal heating, is most effective if a moon's orbit is slightly elliptical, causing the strength of the gravitational tug to vary, creating a rhythmic internal kneading. Additionally, the rocky cores of these moons contain radioactive elements like potassium-40 and thorium-232, which decay over time, releasing a steady, slow trickle of heat. Together, these forces could be enough to melt a layer of ice deep beneath the surface, creating a vast global ocean sealed away by a miles-thick frozen shell. Imagine a cross-section of Titania, the largest moon. You would see a dark, cratered surface of water ice, possibly stained by dark organic material. Below that, a crust of solid ice extending down dozens of miles. Then, a sudden transition, a layer of liquid water, kept from freezing by the pressure above and the gentle warmth from below. At the very center, a dense, rocky core glowing with the faint decay of ancient atoms. This is not a wild fantasy. It is a model based on what we have learned from moons like Europa and Enceladus around Jupiter and Saturn. The mystery for Uranus's moons is one of scale and activity. Are they large enough and warm enough to sustain such an ocean over billions of years? Titania, at about 980 miles in diameter, is certainly in the right size range. Oberon, slightly smaller, is a more uncertain candidate. Their compositions are crucial. A mix of water, ice, and rock provides both the material for the ocean and the radioactive fuel to help heat it. Their distance from Uranus matters greatly. Too close and tidal forces might be too violent, leading to a fractured, active surface like Miranda's. Too far, and the tidal heating becomes negligible. These moons sit in a potentially perfect middle ground, far enough to have stable, solid crusts, but close enough for Uranus's gravity to provide a persistent, gentle internal massage. The chemistry within such a hidden sea would be alien and slow. Without sunlight, any potential life would rely on chemosynthesis, drawing energy from chemical reactions between the water and the rocky seafloor, perhaps where hydrothermal vents seep minerals into the dark brine. It is an ecosystem of profound patience, operating on geological timescales in permanent midnight. For astrobiologists, this makes Uranus's large moons not dead ends, but long-shot candidates, dark horses in the search for life beyond Earth. They represent the possibility that habitable environments are not defined by a star's warmth, but by the hidden interior heat of a world itself, a lesson that the most promising places for life may be the ones we cannot see at all. Every mystery we have explored is framed by a single, fleeting encounter. In January of 1986, as the Voyager 2 spacecraft hurtled past Uranus, it collected all its data in a mere 6-hour window. That snapshot, taken from a distance of 50,000 miles, is the foundation for everything we know and everything we wonder about this tilted giant. The probe's cameras, revolutionary for their time, captured the serene blue disk, the dark rings, and the tortured face of Miranda in stunning detail for the first time. Its instruments tasted the atmosphere, mapped the bizarre magnetic field, and counted the major moons. Yet for every answer it provided, it left behind a dozen deeper questions constrained by its speed, its trajectory, and the technology of an era now decades past. Voyager 2 was a reconnaissance mission, a pioneer on a grand tour. It could not slow down or enter orbit. It flew by at over 42,000 miles per hour, giving its instruments only a brief moment to stare at each hemisphere. This meant it saw one face of Uranus under a specific seasonal light, a planet locked in the depths of its long polar summer. We have never seen the other half of the Uranian system under such intimate scrutiny. The probe's cameras, though magnificent, lacked the resolution and sensitivity of modern instruments. They saw the dark rings, but could not resolve their fine structure or search for hidden arcs. They mapped the major moons, but only one hemisphere of each, leaving their far sides forever unknown. The data on the planet's interior came from indirect measurements of gravity and magnetic fields, a blurry ultrasound rather than a clear scan. Voyager 2 could not peer into the superionic ocean to measure its depth or composition. It could not determine if the faint radio emissions followed a pattern or if the high-altitude heat had a precise source. It saw hints of atmospheric bands and a few clouds, but had no time to monitor their evolution, to watch a storm be born or die. The spacecraft detected hydrogen sulfide in the upper atmosphere only as a tantalizing maybe, a spectral hint too faint to confirm. It catalogued the rings and suspected shepherd moons, but could not find the tiny, dark moonlets that must be maintaining their sharp edges. Every one of the 24 mysteries we have discussed stems from this fundamental limitation, a masterpiece of exploration that was, by necessity, a glimpse and not a stare. The grainy, color-enhanced images from that flyby have a nostalgic, almost heroic quality to them now. They are the first maps of a new frontier, hand-drawn by a robotic cartographer on a one-way journey into the void. They frame the puzzles that have captivated planetary scientists for a generation. To look at those images is to see both a monumental achievement and an invitation, a reminder that our deepest understanding of this strange blue world is still waiting, frozen in time, for the next explorer to finally arrive. Uranus stands as a testament to cosmic strangeness, a world forever toppled, deeply chilled, and wrapped in a magnetic field of pure chaos. Each of these 25 mysteries, from diamond rain to hidden oceans, is not an isolated oddity, but a single piece of a vast, interconnected puzzle. They reveal a fundamental truth that even in our own celestial neighborhood, profound enigmas await just beyond the light of the sun. This pale blue dot challenges our assumptions at every turn, reminding us that the solar system is not a gallery of finished portraits, but a living manuscript still being written. Our journey to understand it has only just begun. The next chapter depends on us. By supporting planetary science and advocating for missions like the proposed Uranus orbiter and probe, we can transform these haunting questions into definitive answers. We can send new eyes to stare into that serene blue haze, to listen to the radio whispers, and to map the hidden seas. So tell us, which of these Uranian secrets captivates you the most? Is it the violent history written in Miranda's scars, the silent fall of diamond rain, or the possibility of a warm ocean beneath an icy moon? Share your thoughts below. As you look up at the night sky, remember that out there, nearly 2 billion miles away, a tilted giant quietly holds its secrets, waiting for the day we are brave enough and curious enough to return.